This video, titled A Continuous Field Foundation for Decision Coherence, explores the gap between when a system works and when it truly understands a problem, treating this gap as a mathematical reality rather than a subjective one. Mission-critical systems rely on equations, not narratives. We are rapidly deploying planet-scale decision engines for governance and markets, often faster than we can establish the governing math for them. As Mary Shaw notes, if AI instantly produces a correct solution, the solution itself tells us nothing about the system's understanding. The real challenge is assessing what the system actually grasps. Performance does not equal coherence. Measuring decision understanding is fundamentally an information geometry problem. Success metrics are often decoupled from the reasoning process. A solution requires constraints that ensure the system remains coherent, interpretable, and survivable. We can conceive of an operating system for thought defined by 4 domains: space, the interaction arena; history, the trail of irreversible commitments; information, the structure of distinctions and ledgers; and time, the budget that turns potential into consequence. No new physics are required for this framework. It relies on standard off-the-shelf physics concepts, including Hilbert space quantum mechanics, Gaige theory, probability continuity equations, and Shannon information theory. Decision coherence is supported by 3 pillars, or conjectures. Conjecture X, the informational floor for bounded systems; Conjecture O, interpretability as an internal gauge constraint; and Conjecture Y, information as a conserved Noether current. Conjecture X establishes the informational floor. For any bounded system, there is a complete, Bell-consistent encoded state. Unitary evolution preserves total information, meaning you cannot fake coherence. The zipper argument against hidden variables shows that denying Conjecture X means denying at least one of 3 established facts: the empirical success of QED, Bell's constraints on local hidden variables, or basic unitary information preservation. Conjecture O demands interpretability as gauge discipline. Different internal explanations can generate identical observable behavior. Without a policy for tracking gauge, interpretability collapses, making a gauge-equivalent description mathematically useless if not auditable. Gauge accountability is a mathematical mandate. Empirical predictions must remain invariant, and the mapping from internal variables to observables must be stable. The system's decision geometry must be fully reconstructible from the recorded state. Conjecture Y defines information as a conserved current. From probability continuity, we derive Shannon information flow. Information does not disappear. It has a calculable volume bulk production and boundary flux. Information obeys local continuity, behaving exactly as a Noether charge. Symmetry demands conservation, and conservation demands continuity. If a system cannot track its information flow, it cannot mathematically claim to understand its output. The continuous form decision map shows that a decision is not a static output. It is a transformation on the information distribution that permanently commits the system to a specific history branch. We can map the geometry of human decisions using an inductor for the internal model, a gyroscope for the coherence tracker, and a predictor for expected futures. High agency demands alignment across history, stance, and forecast. Decision confidence is a calculable object. It derives from the gradient of information, geometric curvature, which is sensitivity to perturbation, and agency. High confidence means stable variation under perturbation. Real systems have finite boundaries, but combinatorially vast internal configurations, a concept we call bounded infinity. Symmetries preserved equal fairness, while broken symmetries reveal algorithmic bias. This addresses the limits of addressability. You cannot track more distinct elements per unit time than information bandwidth allows. Any system with mapping cost approaching 0 will eventually be unable to prove its own coherence. The conservation of consideration states that the total scalar state Q across all agents cannot be implicitly destroyed or created. Failure to account for an agent's stake is a systemic bookkeeping error, not an algorithmic optimization. Precision in meaning is as critical as precision in measurement. You cannot fake coherence. The equations will catch you. Misusing AI writes code to mean understanding no longer matters is a mistake. In summary, the continuous field foundation for decision coherence relies on a geometric framework, treating coherence as a mathematically verifiable state based on conserved information and gauge discipline. Thank you for watching this video.